Okay, welcome to part 2 of the series. So I thought it's worth just recapping briefly what we covered already in part 1. So we had this definition of a system S, where we have a set of states x, we have an initial set of states x0, we have a set of inputs u, we have some sort of transition relation, which we denoted with an arrow, we have a set of outputs y, and we have a mapping h. And we said that we can select an individual state from within this set of states, that the initial set is a subset or equal to the set of states. We can again have an initial, we can have an input u, which is inside our set, and then the transition relation can look like a state under an input transitioning to another state, and here we have that composition of that set, and then we can again have we can denote individual elements of the set of outputs, and this mapping maps from a state x to some output y. And so again here we have this an element of the transition relation where we have x transitioning under the input u to some successor state x dash, and we said that this could be called a u successor or just a successor more simply. The set of successor states can be denoted using post with the input and the predecessor state, which determines whether there's successors or not, and we can use this function u of x to determine the set of inputs to which there are successor states. And all of this is coming from the book Verification and Control of Hybrid Systems by Paulo Tabuada in 2009. So let's cover what we're going to look at in this time. Okay, let's jump back in. So what we're now going to discuss is we're going to discuss system behaviours. So let's consider we have some state which is inside our state space x, and that the initial state x0 is this value x, it fits this requirement. Then every state xi transitioning under ui to a new state xi plus 1 is what we're going to consider here. So if we have this chain of successive states, one after another, depending on whether that finishes or not, we can describe either finite internal behaviour or infinite internal behaviour. So for finite internal behaviour, what we need basically is some sort of stopping point. So here we can consider a series of transitions where we go from state x0 to state x1, state x2, x3, etc., 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 until this final state xn. And that would be finite because we can number the number of states in the transition. For infinite internal behaviour, what we have instead is that we have this counter I is inside the infinite set n0. So in this case, n is the set of natural numbers, so 1, 2, 3, 4, 5, etc., union with 0. So we can have x0, x1, x2, and this will go on infinitely. And so these two terms are very, very important because also we can link them with the different properties. For example, for the non-blocking property, if our system is non-blocking, then any finite internal behaviour we have can be extended to infinite internal behaviour. So let's just draw a very basic system where we have some states, we have some transitions. Here we go, and let's have some initial state here. So x0, we come and we arrive at this state, then we continue here, 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 we continue here. Now, in a finite internal behaviour, we could say at some point that that stops. But if the system is non-blocking, like it is in this example, that internal behaviour can also be infinite because, for example, this loop, we can just go over and over and over, and there's nothing to ever prevent us from continuing within this small system. Another term that we're going to use here is the term initializing or initialized. So we use initialize to describe when the state within the chain, here x0, if x0 is an element of our initial states, then we can say that this sequence of transitions within the transition relation, that this has been initialized because that starting position is the starting point of the system, the initial point. We can also map each of these transitions. So this is the internal behaviour. We can also map it to some external behaviour. And this again can be finite or infinite. So remember, we have our set of outputs. So we can say that x0 maps to some external behaviour y0, and x1 maps to some external state y1, and this maps to some state, and then we have yn minus 1, and we have yn. And so again, we can have this external behaviour that we describe. And similarly, for the infinite case, we can have y0 maps to y1, maps to y2, maps on infinitely. Great. And so now we can describe a set which describes the behaviour of the system depending on whether that behaviour is finite or infinite. So for finite external behaviour, we can describe this set of transitions using B for behaviour, X for this initial state that we start transitioning from, and S. So this behaviour can be described using this notation here. And similarly, for the infinite behaviour, we just put omega at the top. It looks like a W, but this is omega. And we can describe the behaviour from this initial state in both of these cases, infinite and finite. Now, as we've already seen in the previous section, x0, this is just one element of our initial set. But the initial set is a set. And so we can actually, we can get the behaviour and the transitions from each of these states within our initial set. So we can describe a behaviour S as the union for all elements x0 which are inside our initial set, and then we can describe this here. Let me just remove this 0 here. So any state x within our initial state, if we get that set of the external behaviour, then we can describe it. So this is the description of the finite external behaviour again. And we can also, in the same way, describe infinite external behaviour as B with the superscript omega of our system, which is just the union of all the states in our initial state and their behaviours in infinite time. There we go. So for this next part, I'm just going to denote this chain of external behaviours slightly simply. So imagine this underline of the y is to signify that this is a bold y. And so this chain, we're just going to kind of bunch them all up together, and we'll get this behaviour here. Let's make the finite case. So we have this chain here. We can, by seeing the external behaviour, we can, in the case of output determinism, we can identify the states inside of the system. And so how do we do that? Well, it's a simple inductive process. So, of course, we can't see any of these states because they're internal, but because we know the system is output deterministic, we know that if h of x equals h of x dash, well then x must equal x dash when these are successor states. So in this case, we would know that from yn to the minus 1 to transition to yn, all we have to do is we have to look at the set ux, which is the set of inputs which can transition and have successor states for this value. So in this case it could be x to the n to the minus 1. And then for each of those inputs we can just do the transition. I'm going to call it dash dash to not get confused here. And if this x dash dash, if this fits with the h of x mapping that we have, then we know we found the correct one. And similarly, in some ways, this initial output y0, well, there's this another aspect of the output determinism is that the set of initial states, so x0, from the mapping, this set x0 is injective. And so what that means is that for every state inside of x0, it will map to exactly one distinct state output. So we know that x0 is a subset of x, and so in the case of x0, this will map to some subset y0, where y0 is a subset of the outputs y. So this is very useful to us because now we can see this y0 that we have here. So we just need to find the x0, which is inside the initial state, the set of initial states, which maps to this y0, and so then we'll have our initial x0 that we will have found, and then we can follow this process I've just mentioned, and so we can look at all the inputs which, when applied to x0, give us a successor state x1, and we can determine based on h of x1 which of these equals y1. And then from x1 we can do the same thing, and by induction we can take this entire external behaviour that we have, and we can find the internal behaviour that matches it. But again, this is just for the case of output determinism, and so this would work both for finite and infinite behaviour. Another interesting property, looking at the infinite external behaviour, we talked before about how if the system is non-blocking, that then the finite behaviour can be extended to infinite behaviour. Because the system doesn't block, there's always going to be transitions which can be possible. But in the case of a blocking system, it's still possible for us to find infinite external behaviour. So let's imagine a case. I'll try and draw it here. So we have some system with state x0, and it has output A. Now this system has two inputs it can take. One is called loop and one is called stay. Now it's possible even though this state x1 is a blocking state, and when you reach it with stay, you can't move any further, it is possible that you could still have the output behaviour, so this is y, bold y, you could still get the output behaviour a, as long as loop is the input which is taken an infinite number of times. And so here, depending on which of these initial states we're in, just because the system's blocking does not mean that this behaviour for an infinite system will be empty. We can still have an infinite external behaviour even inside a blocking system. Okay, so let's continue. Now, a very helpful property as well can be the inputs. So in this case, we've described the trajectory kind of using u0, u1, but these are all internal. So we wouldn't necessarily know actually which inputs are being chosen, except for that case of output determinism, in which case we can infer the inputs from that. So all we really see is we see this y0, y1, yn to the minus 1, y to the n. And we can't assume that every system is output deterministic. So one thing we can do, which helps with this, is we can define a new system, or a new description of the system. So as you can see here, this system description is very, very similar to what we have before, but we're just adding this small circle notation at the bottom. And what we want to do is we want to include the inputs being used at each point inside of our system, so that we can also consider them to be externally visible. So we have the system, we have the set of states, we have the set of initial states, we have the set of inputs, we have the set of transition, the transition relation, we have the set of outputs, and we have the mapping. So now we can describe this new set as being the set of both the states in the system and the inputs. So you can see here we don't have the small circle because we're talking about the actual system here. We can set the initial set to be the initial set from the actual system, combined with some element. So we're denoting this with a star, but the thing about this element is it's not an input. It's not inside of the inputs. We can describe our updated inputs as a union between the set of inputs and this star. And then we can also describe our updated transition relation. So we have the small circle here. So now what we have is we have a state and the input being almost like a little tuple or a couple here, which then, using some input, transitions to a new x dash u dash, and this is in the system that we've described. And this transition, we say, is only possible if the transition x under the input goes to x dash in the real system. So what we're trying to do is we're trying to just make this input visible within the system. Then we have the updated outputs, which is the outputs and also the input set. And then we also have this updated mapping, which takes both the state and an input, and it returns to us the mapping of that state as well as the input. And so now what we'll have is we'll have two externally visible variables. We'll have the external behaviour, y bar, and then we'll also have the inputs which determine this external behaviour visible to us. So in essence, our external behaviour can now be shown like this, where we now know what u0 is, we now know what u2 is, etc., etc., etc. And so this is really helpful because we can now infer some properties potentially based on these inputs, which are now externally visible, not just internally. That's going to do it for this video. Thanks very much for listening. I hope to put some more videos out soon, but for now, see you soon.